wormholes, and various effects having to do with wormholes. Of course, the simplest wormhole solution is one that you could say it's 100 years old. It's just the Schwarzschild solution, the maximal analytical extension of the Schwarzschild solution. I mean, this full structure of the solution was really only understood 50 years ago by Kruskal. And it has various regions that, just for notation, we are going to call the right exterior, the left exterior, and the future interior and the past interior. So this region looks like the exterior region of a black hole that goes to asymptotically flat space. This is the same thing. And then they share an interior. So both of these black holes share a common interior, and these two asymptotic regions are completely disconnected from each other. Some people use a different notation. They call this region 1, 2, 3, and 4, which I feel it's a very, I never remember which region is which one. And to add to the problem, some people call this the interior, which is really very wrong. So the interiors really should be only this region, or, well, of course, also this region down here. But this should be a second exterior, should be viewed as a second exterior. So that's the basic solution. It's, as I said, very old, and we'd like to understand it better. There are many features of this solution we don't understand. We don't understand what the singularity is, and so on. OK, good. Now, there is a small variant of this solution, which is to have the two black holes in the same space-time. So you have two black holes that are very distant from they're very distant from each other. Then you can find this an approximate configuration, which you can find a solution that at least near each of the black holes looks similar to this one. Okay, the full solution will not be equal to this one. This solution has an SU2 symmetry, a rotation symmetry. This one will not have it because, well, we selected this separation direction. But if you look at physics at relatively short timescales, you can find a solution where the two horizons of these black holes touch at this instant in time, and then they start separating from each other. Okay. So this is, we sometimes talk intertangentially, in an equivalent way between this solution, and sometimes we view the two black holes as living in the same space-time, right? But if you have the two black holes living in the same space-time, this is an approximate Penrose diagram that is valid for, let's say, this region and the wormhole that connects them, but not everywhere. Is that clear?
But the upper one is a static solution, right? And the lower one is a dynamical situation. So in which sense do these compare?
Yeah, so you are right that these two black holes will start attracting each other, and this Penrose diagram does not take that into account. Okay. These two compare for processes that involve, for example, sending a particle from here into this black hole. And then you could have, well, I guess at this point I usually tell the story of Romeo and Juliet. Many of you probably already heard me tell this story, but maybe I'll tell it again. Have everybody has heard the story of Romeo and Juliet? No? Well, anyway. I need one more thing before I tell the story of Romeo and Juliet. So these are some black holes. We'll leave this in the talk. Of course, similar black holes can exist in asymptotically ADS space, and then the diagram will have a similar form. So except that with slightly different boundary conditions. And basically, this type of wormhole exists for any near-extremal black hole. So whenever you have a near-extremal black hole with finite Hawking temperature, you will have a wormhole solution of this kind. These wormhole solutions are not traverse. These wormholes are not traversable, so you cannot send a signal from one side of the wormhole to the other side of the wormhole. For example, if you so before I was asked whether before the point was made that this is a dynamical spacetime, but this is also, in some sense, a dynamical spacetime, in the sense that if you look at the time progression of the spacetime is crunching, and we have a big crunch here in the interior. Okay? And an observer that falls, that sends a signal into the black hole sees that, or that jumps into the black hole will end up at the singularity, and we'll see a time-dependent background here in the interior. Okay? Good. I mean, of course, the configuration has a boost symmetry around this point, but we don't have global time translation symmetry. Okay. Very good. So they are not traversable, but they are almost traversable in the sense that if we send the signal will be very close to the outside, but always outside. I mean, you can really not get to the other side. Now, you might say, well, maybe I do small perturbation, and by doing a small perturbation, then perhaps we'll change the structure of the space-time. For example, we could send some matter here from the left, and maybe it would change the structure of the space-time, or we could have some other fluctuation of this geometry, and then maybe the wormhole becomes traversable. So that could have been the case. But if you demand that these geometries obey Einstein's equations, so if you have Einstein's equations plus the achronal average null energy condition, which is something that we expect should be obeyed. People discussed this in previous lectures. That's the condition that if you have an achronal line, the integral of t minus minus should be, or t plus plus should be bigger than 0. Then those two things imply that it's non-traversable. Okay. Now, it's useful to think a little bit about the connection between these wormholes and the Euclidean black hole. So when you have a Euclidean black hole, you have a Euclidean time circle, which is a circle whose length is the temperature. And then when you look at the radial direction shrinks smoothly, and it has roughly the structure of a cigar sometimes. That's for asymptotically flat space black holes. And it's sometimes useful to draw this diagram looking at the black hole from this side, where we have the circle, the boundary, and then we have this radial direction, rho, going from the center to far away. Okay? So here we have the Euclidean time circle, tau Euclidean, whose period is beta, the inverse temperature. And this diagram has a moment here of time reflection symmetry here at this particular slice. So you can, this diagram is reflection symmetric, and the full metric and functions are reflection symmetric. And that implies that we can analytically continue the solution to Lorentzian signature. So if you have, and the analytic continuation will be real. So if we have some function, let's say some metric component, if t is the normal coordinate here, this is some other t, it's not the same as this time, then we'll find that they will have to be functions of t squared, and then when we continue to Lorentzian, from Euclidean to Lorentzian time, we'll find the same function, but of minus t Lorentzian squared, let's say. Anyway, so when we do this analytic continuation, what we get is this Lorentzian spacetime, and that surface that we highlighted here corresponds to, for example, this surface at this position. And this, of course, was exploited by Hartle and Hawking, for example, to define the state for the quantum fields in a black hole background. They said, well, we do the Euclidean path integral over this bulk spacetime. And then at equal to 0, we will get some wave functional for the fields that we use as the wave functional for the fields in the Lorentzian geometry. And then we evolve that one forwards in times or backwards in times. And in that way, we define the so-called Hartle-Hawking state for black holes. Now, in cases that we also have a boundary description, so we have, let's say, this is an ADS-CFT setup or any situation where we have a duality to a boundary system, doesn't have to have the conformal symmetries. Then we can do the same procedure in the boundary theory. So we can look at this Euclidean geometry, and then we see that here we're doing the Euclidean path integral on a circle at the boundary. So I'm going to draw here another circle. And I draw it separately just to emphasize that this is a hollow circle. This is a circle in which the conformal field theory is living. There is no interior here. There are the degrees of freedom of either the quantum field theory or quantum system that live on this time circle, Euclidean time circle. And we can do this same procedure of cutting at this point, at this moment. But here now we cut just the we cut at this point the boundary theory, and what we see is that we have two boundaries here. So this procedure in the boundary theory will produce for us an entangled state, sometimes called the thermophile double state, which comes basically from considering the Euclidean propagator of the boundary theory. So let's say you start from the state e to the minus beta over 2h. So h is the full Hamiltonian of the boundary theory. So this distance here in Euclidean time is beta over 2, so half of the period of the whole circle here. So a propagator, well, this as a matrix would be this. And then we produce from here, from this matrix, an entangled state by somehow reversing this graph from Bragg to Ket, and we get a state that we can write down as the sum over I. Well, it's really not normalized, so it's proportional to e to the minus beta ei over 2, then I left, I right, and since we turn Bragg to Ket, this is really complex conjugated or time reversed. So we have this particular state in the boundary theory, and then that's supposed to be dual to this wormhole geometry, to this full wormhole geometry. Okay, so I think you probably already, several lectures already used this relationship. I think even myself mentioned it before. But you should, I like now to emphasize how ridiculous this is. And that's when the story of Romeo and Juliet comes. Okay, so Romeo and Juliet were two young people, and they liked each other, but they came from families that hated each other and didn't talk to each other. And so this happens far in the future, so they really confine them to two different galaxies and tell them never to talk to each other. But they can still exchange letters. They can exchange letters. They can exchange qubits and things like this. And they are very smart, and they create, by exchanging entangled qubits, they create a pair of entangled black holes. So a pair of entangled black holes, and they arrange the entanglement pattern to be precisely this of the thermophile double. I emphasize that here the claim that that geometry corresponds not to any entangled state, but to one particular entangled state, which is this one. So if you start changing it, you will have different geometries. So Romeo and Juliet make this particular entangled state, and then they jump in. So here we have, again, well, let me just draw it again. Well, it's really more like an asymptotic. Well, let me ignore the asymptotic difference. And so we have, let's say, Romeo. No, maybe we want to put Juliet this side. They jump in here. And they have to jump at exactly the right time. If they jump too late, they will miss each other. But they can coordinate all that in advance. And they jump each other, and their families sit outside here. And they see them both dying at the black hole. Okay? So they committed suicide. Okay? And that's someone telling the story from the outside would write this. Okay? But on the other hand, they actually meet here inside. And well, they live for a while here inside until, unfortunately, they die at the singularity. So this doesn't have a happy ending. We'll have the Hollywood version later. But notice that the condition that we can view this as an entangled state says that any information that, let's say, Romeo has and wants to give to Juliet is completely inaccessible from this side. So here, Juliet's family can examine this black hole, watch it evaporate, see the ashes, do any quantum information story, analyzing it. Her family will never know what happened here. Okay? Cannot possibly know if this is the right interpretation. I mean, if we have this connection. Okay? And the same is true, of course, for Romeo's family. So this highlights how weird this region here is. So physics is happening here. They can meet. They can have a happy life. But they cannot tell anyone. Okay? At least they cannot tell their families. If, yeah.
What about the evaporation?
What?
So you said that the black holes eventually evaporate?
Yeah. So this is an ADS. Well, here I drew it as an ADS black hole, but you could either couple this to some other system, let the black hole evaporate, let the people here analyze all the decay products of this black hole and so on, and they cannot possibly conclude that Romeo was there or not. So the states where Romeo was there and when he was not there look exactly identical for someone who's watching this evaporate. Okay? And in fact, some people said that this is ridiculous and that entangled states would not look like this. They would really have some kind of fireball here at the horizon, and this will not happen. So it is perhaps possible. So it's a conjecture that something like this will happen, and this highlights how subtle the construction here of the interior should be. Okay? So you might say, oh, well, they're entangled. Some people say, well, this is completely understood because all we need to do is just evolve the bulk equations to this slice, and then we reconstruct we reconstruct operators here on the boundary, and so this is completely understood. And yeah, if you do that, that procedure is understood, but you have not understood what's the origin of these bulk equations that you use to translate something here to this slice. And part of, I think our goal should be to understand where those bulk equations, how those bulk equations arose and how we got this strange behavior. Okay. So that's the story of Romeo and Juliet. Now, the new thing that we are going to spend most of the lecture talking about is a new effect that happens when you start coupling the two sides. So, I mean, clearly, if you look at both sides, and so these families somehow start communicating with each other, they can conclude that they perhaps met, and they can even time evolve this state to the past and do other things that they wouldn't do if they cannot communicate with each other. And so now we'll look at one of the simplest, a very simple communication they can have. We'll consider the same setup of the wormhole. I guess I will be drawing this drawing many times. And we are going to consider a simple interaction between two fields, some field connected here at the left side and some field connected here at the right side. So from the bulk, so we're imagining adding this interaction. So let's say phi left at, let's say, some time, let me call it 0, and phi right at 0. So we're adding this operator in the time evolution, in Lorentzian time evolution of this system. Okay? And this is a setup that was considered by Gao, Jeffries, and Wall. And Gao is here, sitting somewhere here. You can ask him more questions about it. Okay, so we have this setup. We are considering, let's say, a bulk field here, phi, that exists everywhere in the space-time, but we're imagining this as an interaction we set up in the bulk between the field operator here and the field operator there. Of course, this looks weird from the bulk point of view because it looks a bit non-local. But this corresponds on the boundary theory to some interaction where we have G times the corresponding operator O left. So this is the operator in the boundary theory that corresponds to the bulk field phi. And then we have also the operator O right in the other field theory. But nobody forbids us from taking two decoupled field theories that maybe happen to be in this particular entangled state and adding this interaction to their Hamiltonian. Okay? So it's a perfectly legal interaction. Now, in order to make the effects we're going to talk about a bit larger, we are going to consider several fields, and so where we go from 1 to k, and then the corresponding operators going from 1 to k. And so we're going to consider G to be reasonably small, so that for each field we can treat this as a small interaction, but then the overall effect, which I'm going to describe in a second, can be made larger. Okay. So this couples the two sides, and it's clear that because now the two sides are coupled, if we are sending something from the left side, it might show up on the right side. So the commutator between an operator here and an operator here on the right will be non-zero. So before, when we didn't have this interaction, it had to be exactly 0. So that notion of locality, because it comes from an entangled state, should be exactly 0 when we had no interactions. Now that we have interactions, it can be non-zero. And there is a simple way in which it can be non-zero, a trivial way. Let's say we send here some field phi, one of the fields that appears here. Well, this field can, it can be picked up by this operator and then transferred to the other side. And then we here we'll see a non-trivial commutator between the field phi and, here on the left and the field phi on the right at a later time. So this is this can suddenly happen, and so we're not surprised by this. This is what we would expect, and nothing mysterious. So now we look at the more interesting process where we send, let's say, a different field. Let's say we send a field chi. We have a bulk field chi, and there is a corresponding operator chi. Let me denote them by the same letter. And you send this one. And of course, well, so we have this other interaction. And now the crucial observation for analyzing this problem is that when you have this type of non-local interactions in quantum field theory, you can have negative energy. So you can create negative energy. So let's analyze this just in flat space first. So this happens whenever you have any non-local interaction. So imagine you have a quantum field theory now in flat space, and you pick 2 points, and you add an interaction like that one, where we have a field here. This is the field left, and then here we have the field right at 0. Okay, very good. And now we are going to try to evaluate the stress tensor. So we have the stress tensor T, which let's say is d phi, and maybe some other terms. Okay, good. So let's say we want to evaluate the stress tensor somewhere here. So in the Lycon, of course, so somewhere here we want to evaluate the stress tensor
So at the point, let's say that the space like separated from this point.
Then we evaluate the stress tensor. Well, I'll do it in this blackboard to write bigger. So we evaluate the stress tensor in the state perturbed by this operator, and we'll get that the leading order term comes from the expectation value of the commutator of the stress tensor, T mu nu, with this double trace interaction, phi left of 0, phi right of 0. Okay. And then we put in here the expression for the stress tensor, which is some quadratic expression for the fields, right? Now, the commutator, so if we put it at space like separated from the point on the left, there will be no commutator between this point and that point, okay? So now we evaluate this in the free theory, in the theory with g equal to 0, so there will be no commutator there. So the commutator should come from this point to that point, but we put this point, let's say, in the forward icon of this one, so there will be non-trivial commutator, or we could be at the lilac separated. So there will be a non-trivial commutator, so there will be some commutator between one of these d phis and phi r, right? So this is just some C number, and then we'll have the expectation value of d phi and the operator on the left. And these two, we expect them to be non-zero, so this will be something non-zero here. And we multiply all of this by g. And so if we, because the effect is linear in g, we can choose the sign of g in any way. So if we get something non-zero, we can get something either positive or negative. Okay? And by adjusting the sign of g, we can make the energy negative. So, yes?
This makes it seem like it's very easy to get negative energy.
Yes.
Is this a statement about the state being special? Or
yes, yes, yes. This shows that it is very easy to have to create this negative energy. But if you allow these non-local interactions in the Hamiltonian, right? So
how fine does it have to be?
No fine tune. So well,
You have to couple things which are entangled.
yeah, you have to couple things which have non-zero correlations. So if you couple two fields which are not correlated, this will not work, at least at this order. So if you view this as some way of creating some state, you look at the state here, certainly some state with negative energy. I mean, this also creates a pulse of positive energy that way. So the total energy, of course, of the state you create will be positive. But notice that this is a process that cannot be done by unitary time evolution, but local unitary time evolution in flat space. So if we are in flat space and you have a local Hamiltonian, you will never get a term like this in the Lagrangian. Okay? But in the ADS context, we can have a term like this because from the point of view of the boundary theory, we can certainly have it. And later we'll discuss how we could have it when we think about, for example, a black hole or black brane that lives in flat space. And, well, maybe I could say it right now. So if you have two black holes that, let's say, are entangled, you can, let's say they have a wormhole that connects them. And if you bring them close to each other in the ambient space, they might exchange some fields and in the flat space region and generate an interaction of this kind. Here I put the interaction at exactly t equal to 0, but we could imagine this interaction smeared over some time of order the temperature here of the right black hole. So we can smear it a little bit, and we'll implicitly consider that so as to avoid any UV divergences that might arise. Of course, if the boundary theory here is quantum mechanical, then there are no UV divergences, but so those are little details that don't affect the gist of the story. Okay, so now we arrange this so that we arrange this interaction so that we have a negative energy pulse that goes here into the black hole. So we have some negative energy. And then this particle comes in here, and Normally, if you had positive energy, these particles suffer a time delay, would get deeper inside the black hole. But this particle now suffers a time advance and now emerges outside and can be picked up by the right observer. So we can send the signal from the left to the right, and the signal goes through the wormhole. So there is no apparent interaction between chi and phi in the field theory in the bulk, but the interaction is via the gravitational effects, the negative energy produced by these particles. This type of interaction is, of course, exactly the same interaction that Douglas was talking about, the shockwave interactions. Yeah, and this effect, at least to first order, becomes larger when you separate these two by a long time. Okay, so separate by time more or less of the order of scrambling time, and then you can have enough to go to the other side. I mentioned that we needed large G and K, small g and large K in order to make the effect large. And so that's what we are talking about. We are have enough negative energy to be able to come out on the other side.
How can you see from the boundary if the chi is getting on the boundary?
Right. So you can ask how, yeah. So you can say, okay, so here we see this process in gravity, right? So we understand it in detail in gravity. And you can ask, well, can I see this in any explicit quantum mechanical model that this happens? Okay, I'll discuss that in a second. So let me see. Before I answer, yeah.
You do have to do a complicated operation to go back into the past to send the...
Well, here we imagine that we send the signal in the past, and then we act on this operator at some time. Yes, if you were sitting here, you would have to do a complicated operation. But here we imagine that we had this entangled state. Of course, we could create the entangled state here, and then we have to go back to the past. You have to do something complicated. Yes.
So it's not a simple thing to do.
No. But yeah, you evolve here backwards in time. You send this, right? And then you can do it. But it's not exponentially complicated, if you wish. So you might have to evolve backwards in time a little bit. Before I discuss how to see it in the field theory, I'll answer your question. Let me just mention the twist to the Romeo and Juliet story. So here the idea is that if their family somehow so they see Romeo and Juliet fall into the black hole, and then they decide, they realize, oh, maybe something bad happened. And if they communicate to each other, they make peace. They can actually add some interactions here and put them out of the black hole. Okay. Anyway, so now let's answer the question that about how to see this in a field theory, and we'll see how to see it in the SYK model. Yes. Sorry?
The families, will they be able to turn on the direction?
Yeah, they could do that. It requires them to act fast enough and be relatively close. It's somewhat difficult for them to do, but we'll discuss a little more what they should do when we discuss teleportation. There's a slightly more realistic way to do it. Well, of course, once the two families start communicating, they could do very complicated things, evolve the two black holes backwards in time and remove them. So this is just a slightly simpler version. Okay, now, so what's interesting about this discussion is not that the signal goes between the two sides, because they were coupled, so we in principle know that there can be signals that go, but what's interesting is how the signal goes, that it goes through the wormhole and allows us to explore a little bit of this interior region. So I'll make this point more clear now. So let me discuss in the particular case of ADS2. This could be ADS2, or it could be a higher dimensional spherically symmetric ADS, where the interactions that we put here are spherically symmetric. Okay. So in that situation, the shock wave. So normally when you go to through a shock wave, you might see some tidal forces because the shock wave is not completely uniform in the transverse dimensions. And you might feel uncomfortable depending on the size of the shock wave. But if you produce a shock wave with these spherically symmetric situations, then the physics is similar to these shock waves in ADS2. And there, the shock wave is basically like a coordinate transformation. And so there is no local, you don't feel anything when you go through one of those shock waves. Okay? So one way to describe the ADS2 situation is to say that we had these motions of the boundary that we were discussing. So this is the original black hole. Corresponds to the portion inside these boundaries. And then this is the signal that we send, the chi signal. And now we act with the field operators at this point. And the basic here you can view this interaction as inserting in the path integral. Well, that operator, I'm just rewriting what we had before, phi left, phi right at 0. And we can approximate this time evolution by taking the expectation value of these operators in the exponent. What that corresponds to is to saying that we have these two boundaries, and this interaction generates an effective potential between these two boundaries that is set by these correlators. So, and to lead in order, when we have small g and large k, we are summing here over I from 1 to k, and k is large. This is the leading effect that we will have. We will have this potential between these two boundaries. And the potential, if g is appropriate, has the appropriate sign, positive, then the potential will be attractive, and the kick that this boundary trajectories feel is towards the interior. And so these are the new boundary trajectories. Here I'm just describing exactly the same thing that we described with shock waves, but in this ADS2 language, to show that it's even simpler. So it can all follow from the symmetries of how these boundaries move and the little kicks that they receive. And so now we get the signal back here on the right, and it's been teleported through this wormhole. And this person, let's say this guy was some person, or let's say a cat. The cat emerges in the other side, having explored an empty wormhole. This cat never saw anything inside. Okay, so now this description of the physics in ADS2 is related to the dynamics. So the dynamics of this boundary is the dynamics of this Schwarzian variable. And here, when we compute, for example, the correlators between a field here and a field over there, we can think of these fields as moving in empty ADS2. So their properties are determined by SL2R symmetry, right? By the SL2R symmetry of ADS2. So that implies that this whole calculation, we have a complete parallel in the SYK model. So in the SYK model, if we do exactly the same calculation, where now instead of phi, we have fermions here, and those are the interactions that we have here, and then we send another fermion through here. This fermion is some field that will have conformal correlators, but will have these boundary reparametrizations that we discussed, that with this Schwarzian action I spent some time discussing, and the dynamics of that will be exactly the same as the dynamics we have for these boundaries, and the results and the formulas will be identical. So that's an example where you see this effect in the SYK model. Yes?
When you turn on this potential, does the point solution change?
Yes, yes. So what changes instantaneously is the trajectory of these boundaries. And
is the at time 0,
right.
the earlier trajectory and the later one, would they go smoothly?
No. There is a change in well, I don't remember the order of derivatives, so it's a fourth derivative equation. So maybe it's the third derivative that changes. I just don't remember now. But this changes, and the net result is that you get this new trajectory that might have a different energy. The energy or temperature, effective temperature, is not important. What's important is that the red trajectory differs from this one in part by an SL2R transformation, by one of the zero. Remember when we discussed the small perturbations of the Schwarzian theory, when we do a small perturbation, we can turn on these zero modes that come from acting with an SL2R transformation, and one of them grows exponentially in time. So the one that grows exponentially in time is the one that lets us enhances the displacement here and allows us to see the signal.
You said it's a third order equation, so do you need...
Fourth order.
Okay.
Yeah.
Do you need one or two extra constants to say how the older and the...
No, how this match comes from the rules of the game that we outlined before. They come from these SL2R symmetries and so on, and we can explicitly compute it. I'm not giving you the details of how to compute it, but I think we discussed enough computations last time to see that computations of this kind could be done. Well, maybe if you insist, we can give some details. Well, how are we doing with time? Oh, we're not doing too bad. No, yeah, we're doing pretty badly. Yeah, I think I won't give the details. But last time we discussed that in order to couple to the Schwarzian, we just take the correlator and we make a coordinate transformation of the correlator, and it gives us some effective action for this Schwarzian variable. And then we do the path integral over the Schwarzians, and then that's how we compute this. And we can compute that just perturbatively and so on. So it's not a complicated calculation, but I won't discuss it. So the point is that this lets us explore a little bit of the interior, but of course we only can explore so much. So we can explore up to here, and then if there is some signal that goes in here, we'll never be able to extract it. Okay. So it's nice that we can explore part of the interior, but there is something that is slightly disappointing, which is the fact that we had these singularities here, and when we do this process, the singularities have also moved. Okay. So it doesn't let us go any closer to those singularities. So it's a bit like the story that there is a pot of gold at the end of the rainbow, and then you're just trying to go to the end of the rainbow, and the rainbow has moved. Okay? What? Yeah, it's true. Also true about this horizon. I mean, the region you cannot see has moved. Okay? And so we have the pot of gold, which is, of course, the singularity that will let us understand the beginning of the Big Bang and all that. And it has moved a little bit. So anyway, we have to do something more clever. Okay. Now, in what we discussed so far, we had a quantum interaction between these two sides. And if, let's say, Romeo and Juliet's family want to try to set up this interaction, they have to exchange qubits in order to set this quantum interaction. And they can do it. They can do it. But there is something else that one could do in order to send the signal from here to there, which is to, instead of setting up this interaction, you can do a measurement here. So you can do a measurement. We can measure the value of the field. Let's say you measure the value of the field phi I, and then the eigenvalue of the field gives some value sigma I. Of course, for an actual field, there is large fluctuations, and there's an infinite number of values. Let's imagine it's a qubit, or you divide the field range into little pieces, and then you measure those things. And then the person on the right just sets up the interaction by taking the value that was measured for the field I, and then acting with the operator phi I just on the right side. Okay? So we get this, and this interaction, again, in average, will produce the same effect on the right that this interaction was producing, because we could have had this interaction and, let's say, measure the field just slightly afterwards, and we would have essentially the same answer. Now, the answer here for the right observer will be different, because the process of measurement introduces some energy, and we'll end up sending some stuff inside, and the actual trajectory for the left observer is different. But the fact that remains is that the right trajectory is pulled inwards, and that will be the same. So we get the same effect, and that's an example of quantum teleportation. So let me review now quantum teleportation and discuss how this gives us a geometric picture of quantum teleportation happening through the wormhole. So if you think that, let's say we have the proverbial Alice and Bob, and Alice wants to send Bob, who's far away, a qubit, then how much information should you send to send a qubit? Well, a qubit is the state of a pure qubit is given by a point on CP1, right? And so there's an infinite number of points. You naively need to send an infinite amount of information because you have to say exactly where this qubit is pointing. Of course, you could send it approximately, but let's say you want to send it exactly, you would need an infinite amount of information naively to transfer a list of classical information. However, let's say we have Alice and Bob here, and they share, they previously share an entangled qubit. So they arrange in the far past, they exchange a qubit, and which is forming a Bell pair. So this is an entangled qubit in a Bell pair. And then comes the message qubit that, let's say, Charlie might give Alice, and Alice now wants to send this qubit to Bob. Okay. So teleportation consists in taking this message and the entangled pair, and doing a unitary transformation that mixes these two sufficiently, and then doing a simple measurement, let's say, in the sigma c basis for sigma 3c for each of them, sigma 3 for each of them. Well, I guess this is sometimes called C, the qubit operator C. You get the measurement, so you get two classical bits. And then these two classical bits are sent to Bob, and then Bob takes his qubit and applies some transformation B that depends on the values of the classical bits. So it has some control knobs that depend on the values of the classical bits. So there are 4 possible V's that Bob could apply, and then out comes the message. Okay, so that was the setup for teleportation. And so here, it's important that you choose an appropriate U. And so what is the basic property that U should have is the following. So we know that U is a unitary transformation that transforms the space of 2 qubits into the space of 2 qubits, right? But we want another requirement, which is that for each values of the measurements here, which are 4 possible values, U is also a unitary transformation from this input to that input. So now we view this not as an input, but as an output, and then we want a unitary transformation from here to here. And such U's can be found. Okay, so I won't give you the explicit form. Maybe some of you might have seen it. You can maybe look them up in Wikipedia. But such U's exist, and that's the basic property. Because once we have this property, then the V that we should choose is just let me call the U that we get this way, U tilde, okay? It's because this is now the input and this is the output that depends on these control knob parameters. Then V should essentially be the dagger or the inverse of that unitary operator. And so we take the message, this does something to the message, and somehow in some ways the message is traveling here up to here, then we do the inverse transformation and out gets the message. So that's classical teleportation. So here we have a similar story. We take this diagram that we've been drawing many times. So this is the initial message, okay? This is the message. The time evolution up to here is the encoding operation U that has to have that property, and for that it's important to mix up basically the message with the rest of the entangled states sufficiently. If you mix them up sufficiently, you typically will have that property. Then we do the measurement here, and we transfer. So here there is the action that Bob does together with the time evolution is the decoding operation, or what we were calling V, and out comes the message here on the right side. Okay, so those are the steps, so the standard steps of teleportation, how they look like in this diagram. And yes?
But still, to do this teleportation, they need to send the classical signal, no?
Yes.
But they already separated.
Yeah, so the classical signal goes, so here you do a measurement, and the classical signal goes through the laboratory, right? You imagine that this is like some condensed matter system that exists in the laboratory. There is a condensed matter system here, and another condensed matter system here, and they are in a complex entangled state, in the thermophile double entangled state, and then you are doing this experiment. You send the signal to one, you perturb one by sending the message, then you do the measurement, right? Then you take that message from one to the other through the lab, right? Yes. So So how do we do that in space-time? So you can imagine that the part of the diagram that we drew over there is so we have two black holes that are connected by some kind of wormhole, right? This wormhole region is this part of the diagram, and then you do some measurement here out of this black hole, and you, let's say, take it to the other black hole. And in order for this to work, you need that the time it takes you to go from here to here is small compared to the time scales of this process, of the evolution of this black hole. But if these are very close to extremal black holes, right, the characteristic time scale for evolution here is the inverse temperature. And you can take that inverse temperature to be huge, very, very large, and larger than the separation between these two black holes. And if you do that, then this signal can be transmitted almost instantaneously. So that's one way in which you could set up this process. We'll later maybe discuss that in a little more detail, but that's the basic idea. Any other questions? Yeah.
You're using time translation variables here, but is there still somehow any interpretation in Euclidean signature?
Euclidean interpretation, Euclidean. Yeah, all of this is a Lorentzian picture. So with the initial discussion that I had for Euclidean signature was just to explain why we expect that the thermophile double is given by this geometry, by this wormhole. That was the motivation for the statement. But this whole thing is done in Lorentzian signature. You can very well ask, is it easy to do the wormhole in Lorentzian signature, right? Because usually we cannot prepare states by doing Euclidean time evolution. So we don't have a machine that allows us to do Euclidean time evolution. So you can ask this question, and people have tried to come up with different ways, and I'll discuss one way to produce the thermophile double in some simple systems later, hopefully. Yes?
In the original teleportation, once Z is measured,
Yeah.
Alice and Bob are no more entangled. Is that correct?
Yes, yes, yeah. Good point. So yeah, I guess I didn't emphasize this, but here Alice manages to send Bob 1 qubit, just sending 2 classical bits. So not an infinite amount of information, but the 2 classical bits. But they had to spend this entangled qubit. So the process costs 1 entangled qubit, and yes.
What happens in the eternal?
Yeah, so here also this process should reduce the entanglement between the 2 sides. Yeah.
Is there some limit to the amount?
Very good question. Yes, yes. Yeah. So the question is, so here, of course, I mean, if you send just 2 qubits, it's clear that you cannot send an arbitrary long message. You can just send 1 qubit message, right? If you send 2 classical bits. So the limit, the first limit will be, since here the amount of entanglement is really very big, it's the black hole entanglement, so we're not going to be limited too much by that, but we're going to be limited by the size of message that we're sending. Okay, that will be the main limitation. And let's see where that limitation comes in, and it's easier to see in this diagram. So here, when we drew this diagram, I neglected the fact that when you send a message, this boundary gets moves a little bit, right? So if we try to start sending, let's say we fix the size of the measurement here. Little m is the measurement. Then when you try to send a very big message, what will happen is that the trajectory of the boundary is bent, and it's not going to follow this trajectory, but it's going to follow a trajectory which is further away from, it's bent outwards. And then what happens is that here they look very close, but they become more distant, and the correlations get reduced. This is similar to the shock waves that Lenny was talking about. So when we send this, we send a shock wave that decorrelates the 2 sides. Okay? And so it decreases the correlations between the 2 sides, and that implies this will be smaller, and it decreases the force, right? And because of that, this will not be bent inward so much. It's limited in how much it gets bent, and for a large enough message, you lose the ability to go through the wormhole. And parametrically, it has the right scaling, but the factors of 2 and pi or the 1 factors are not clear. Yeah, because it's
the right scaling?
The amount of information in the message relative to, so there is a bound on the size of the message relative to so the size of the message in qubits should be less than the number of qubits in M in the quantum message should be less or equal than the number of bits, so the number of classical bits. So this is the bound that we have just under general teleportation, and then we can check it in this situation. So we can imagine that each of these fields is roughly like a Pauli matrix, so it's 1 bit. And then the size, the amount you can send here is limited in this way.
If I have as many fields as I like in the exponent there, then I think I can send as much as I want.
Yes. Having more fields, so roughly in this estimate, the number of classical bits goes like k. So then it's a statement that as k gets larger, you can send more qubits, but not more than k. So if it's tried here to send more than k, then the amount of bending you get here is so large that you cannot recover it here. Of course, you can send k here and then put here with k prime much bigger than k, and then you can do it. But,
up to a message which is as big as the black hole.
yeah, up to when it gets to be of the order of the black hole, then something else will Yes.
When you have the schematic for the 2 black holes in Spacetime as a
Yeah.
visualized, is that supposed to be implied by the fact that once you have in the boundary the ability to talk to the 2 sides,
Yes.
that you need that in the geometry? what
Yes,
what's
so
the classical channel?
So this is just the effective description of the wormhole region, right? Here we are not saying how we generated this interaction. This is a more detailed, complete discussion where we have the black hole sitting in a bigger space. It includes more things, and it includes how we generated the interaction. Yeah. Yes?
If the measurement there is a projection,
Yes?
do we get a partial firewall at time 0?
No, you are just doing a projection here, and then you can send doing the projection will send some excitations here into the black hole, but no firewall. Okay, very good. So that's the connection to teleportation, and now, well, one interesting thing about this is that in teleportation we don't get a very clear picture of how the qubit goes. But here we get a very nice, at least for this particular state, we get a nice clear picture. Yeah. So maybe, yeah. Well, here I was going to say a vague remark, but maybe I'll skip it. Well, maybe I'll say it anyway. So it might be that the bulk, I mean, we in the whole set of lectures here, we've said that the boundary is more important. There's it from qubit, the bulk from the qubits. But maybe it should be the qubits from it. So it should be the bulk knows a little more. And then when we put boundaries, the bulk might be some kind of topological theory, some theory we don't completely understand. But once we understand it, they will be very powerful. And it's not quantum mechanics. And when we put boundaries, we get some degrees of freedom on the boundary, which are quantum mechanical degrees of freedom. And so we get quantum mechanics from it. Okay. End of vague remark. Okay, so yeah, one more point. Well, maybe this already, I already said it. Well, maybe I'll say it again. Notice that, so when you send here the message, and you send it really relatively early so that it can be extracted. So it's fairly scrambled when it gets to this point. And the commutator of the measurement operator, and u, the message, u minus 1, u is the time evolution from here to here, that is non-zero, okay? So when you do the measurement, you somehow have destroyed the message. So the message is not recoverable from the left side. So if you did this measurement and then you say, oh, I forgot, I want to extract the qubit, you are not going to be able to do it. When you try to evolve this backwards, this extra energy that comes in also comes into the back and bends this trajectory in this way so that it makes this message unavailable. But the message is there, and if this is there in the interior, and if this M is sent to the right person, so the person that is entangled with the interior, then that person can extract the message, right? And the interior knows about this, knows that despite the fact that there is this naive commutator, someone who's entangled with the system can extract the message. So the interior is somehow wise. So of course, all of this is for a particular entangled state. It would be nice to understand the general picture of this whole story. Okay. So now I like to discuss the Hayden and Preskill paradox, or apparent paradox. Okay. So this is, I think the paradox goes to Susskind and Thorlasius, and Hayden and Preskill gave a nice analysis of this. So the idea is the following. So it's a conflict between unitarity and the non-cloning paradox. So we imagine that we have a black hole, and let's say Alice sends a message here into the black hole. So the message here goes in, and then Bob, let's say, watches the black hole evaporate and can extract, in principle, the message that Alice sent. Okay. But now the message seems to be in two places. It seems to be in this Hawking radiation coming out, and also in the black hole interior. Okay. So we seem to run into trouble with the non-cloning paradox. But then you say, well, maybe what is in the interior stays in the interior, so we don't care. However, Bob could decide, after gathering all this information, can decide to jump in and look at these two qubits. So for example, Alice could have ensure that the message could send a robot, so that the robot sends the message in this direction, and then Bob, jumping it later, will see two copies. One, the part that he decoded, and the second is the one that was sent by the robot. And the resolution of this paradox was based on, let's say, the Trans-Planckian problem. So the idea that it would take so much time to decode this message that you would have to send this with humongous energy, and you could not really do this. Okay, so that's that looks good. But what Hayden and Preskill ask is how long would it take to decode the message? And so they said, well, let's look at the most favorable situation. So in principle, it looks like decoding the message is a very, very difficult task. You have to gather all the Hawking radiation, and out of this Hawking radiation, decode the message. But what they realized is the following. Bob could have been watching this black hole for a very long time, and so we have the black hole, and here is Bob with an HP computer, and this stands for Hayden and Preskill, not Hewlett-Packard. And maybe this is an old-fashioned. I think now no one has a Hewlett-Packard computer. So what this computer did is it collected the Hawking radiation of the black hole and produced it's a quantum computer, and produced a state in the quantum computer that is maximally entangled with the black hole state. So we have the black hole, which is represented by that diagram, and is maximally entangled with the Hayden-Preskill computer. And now, in this situation, we could say that really the computer has almost has perfect control on what the initial state of this black hole is. And then Alice sends the message. So after this, Alice sends the message, so the message goes in. And Bob then measures a little bit of Hawking radiation coming out of the black hole. This is Bob measuring that. And so he takes a little bit, so the message goes in, takes a little bit of radiation, and feeds it to the HP computer. Okay? And the claim is that immediately after receiving this radiation, we can get the message that Alice sent. And the important point here is that the amount of radiation that Bob needs to get is the size of the radiation, or the number of qubits of the radiation, has to be just slightly bigger than the number of qubits of the message. Okay? So this is fairly surprising, because naively you would have thought that, well, you send a message, you need to get at least all of the black hole radiation, or maybe half of it. But the information comes almost immediately out, because, and they call these black holes as mirrors, in the sense that after this time and in this setup, the information should come out immediately. And so that's a very strange effect. Of course, it has to, in order for, so I didn't explain why this is possible. They had an argument for why this is possible. And let me see if I have time to, well, I'm going to just simply give, should I explain the argument? Yeah, maybe I should explain the argument. Well, maybe I'll say the argument in words. So the argument is that we start with a Hilbert space, which the black hole is, there is a black hole worth of Hilbert space here, and it's also in the computer. There is the message. Now there is a slightly bigger Hilbert space here. And then there is the radiation, which is slightly bigger than the message. And so by the time that the radiation is fed here, the HP computer has access to the radiation and the initial black hole, which is more than half the system. And if you have a random state in more than half the system, a random pure state, then you will be able to find in the rest of the system something that is, well, for this to be correct, we have to have a copy here of the message. So we will be able to find in this system some qubits that are perfectly entangled with some qubits that were entangled with the message, and in that way we can understand that we got the message. Maybe this was too quick. You can find.
I just didn't understand why you need to observe this paradox. Like why don't you just say that? I mean, right from the beginning, if there is cloning of this,
Yes. Yes.
this is already paradox. Why do we need to?
Good. Well, the question is whether we should worry about having cloning where there is one piece inside the horizon and one piece outside the horizon. You might say since the region inside the horizon is not accessible to the outside observer, there is no problem. Maybe the way no cloning works is it works so that there is no single observer that can see all of them. So that was a hypothesis here.
That's like a mathematical claim that just cannot happen. So
Well, I kind of agree with what you are saying, and we are going to see that that indeed, well, ask your question a little later. Here the philosophy was that maybe there is something mysterious in which things work, and maybe the message can be copied, but as long as no two things, as long as it's not possible for someone to check that there is a contradiction. And here it was impossible to check thanks to the Trans-Planckian problem. Okay, so now in order for this to work, we assume that this was a very generic state, and for that we need to send the message here early enough so that it is scrambled by the time that Bob does the measurement. So you need to send the scrambling time, and this implies that, again, for the same reason we discussed here, you would need to send a Trans-Planckian signal. And so that was their resolution of the paradox. But we'll see that actually there is another way to think about this. Where is it? Okay, anyway. The other way to think about it is the following. So we start with the black hole. And then we said that the HP computer made an entangled state and so on. So we are going to imagine a quantum computer that will make an entangled state which is actually the thermophile double. So inside the computer, there is another black hole. And so this black hole is in Bob's quantum computer. And if he puts it in this state, the full geometry will be this one. This should be a straight line, sorry about the drawing. And so that's what we have. Something offensive about the horizon that bends. The boundary might be bent, but the horizon. So that's the message that Alice sent, right? And then there is the measurement of the Hawking radiation that Bob did. And then he feeds it into his computer. And then the process of feeding it to the computer, we can think one process that he could do is he could do this Gauss-Jeffreys wall process. And if he does that, then the message, well, there is the shock wave, and the message comes out, right? The message goes in here, and it comes out. And in this picture, the message is never copied. So I think this answered the question in a way that is satisfactory for you. And so what we see is that so here what's important is that we need to include the space-time created by Bob's computer, okay? So the whole process of extracting the message, in the original discussion here, we were imagining that somehow Bob was sitting here and was extracting the message by doing some funny operation here, and we didn't describe the space-time that this funny operation was creating. And the idea is that once we include that space-time, at least if we create this particular state, then the message is extracted from the interior, right, through the wormhole, and it gets to Bob. And in this way, it's never copied. And the resolution of this paradox look like, well, there is some kind of transaction where the message goes from the interior to Bob and so on. And it's somewhat illegal, but it's beyond what the bulk theory can reach. So there is a bulk policeman, which is the effective filter in the bulk. And this transaction happens beyond the reach of this policeman. That was the picture here. Instead here, the picture is that in the bulk, everything happens according to the bulk. The bulk policeman has no problem with this transaction. It is perfectly legal and perfectly fine. Okay? So that's this picture here. Of course, it works only if Bob made the thermofield double. Now, you can ask, is there any other way in which Bob could extract the message? Is there any other process? The idea is probably that any other process that he would make would somehow connect the computer to the region here near the interior. That's the idea. Now, I like to just point some similarity between this type of resolution of this paradox and some other problems in, let's say, statistical physics and so on. So let's say the Maxwell demon, right? So if you take the Maxwell demon, it seems to imply a violation of the laws of increase of entropy. But once you include the entropy of the demon, of the machinery that drives the demon, then there is no resolution. There is a resolution. I mean, the entropy increases when he erases his memory and so on. And here, I think the lesson is that we need to include the space-time generated by the quantum computer. So any quantum computer that is doing a complex operation is generated some space-time, and this space-time can be connected to the system you are interested in through the interior, so if the system you're interested in has a black hole solution, it might be connected through the interior with some other system that might be distant and so on, and you need to take into account those connections. So it's important to understand the entanglement or the pattern of connections between these two. It's probably, as Lenny was explaining, it's more than entanglement. You probably need to understand the complexity to understand the length of this wormhole and so on. And all that is part, well, here we understood this in one specific example, very simple, but I think the lesson is likely to be more general, though we don't have the general picture. Okay. And just for your entertainment, I've set up outside the lecture hall a perpetual motion machine. And your task will be to understand the resolution of why the laws of entropy are violated. Okay. Now, let's continue this analysis a little more. So there is a fun thing. Yeah.
Is it your thinking that the Hayden-Preskill resolution is really wrong or unnecessary, or is it an alternative description?
I think that this is the previous resolution relied on the unknowability of trans-Planckian physics. Yeah. So it relied on being beyond the reach of the law. And this resolution is in agreement with the law. So I like this as a more lawful solution of understanding the bulk. Yeah.
But the Hayden-Preskill solution was a tight fit, a fairly tight fit. That
yes.
Scrambling time in one place, and that was just barely enough to rescue you.
Yes.
So that seemed attractive just because it was a tight fit. Is that just an accident?
Yeah, well, I think it's not an accident because in order to extract the message, you need to be a scrambling time here. Yeah. No, it's the fact that the scrambling time appears is not an accident, and it's an element of this discussion also. Yeah, it's in a different way, and I think, well, I view this as a more satisfying solution because it is in accordance with the laws of physics in the bulk. We are learning we don't need to modify the laws of physics in the bulk to understand this extraction. Now, we might require some modification in order to understand how the wormhole gets shrunk, right? So if the black hole is entangled with the quantum computer, you will have a very long wormhole. And in order to extract the qubit, you'll need to shrink it. So what is the process that shrinks the wormhole? Well, the general process might be very complex. We saw the talk by Aronson, who talked about the Harlow-Hayden complexities problem, I mean, the hardness of solving this type of problems, and it's possible we might not get a nice picture for that. Maybe what we need to do is create some interference pattern between wormholes, and then in the space of all possible wormholes, they interfere, and suddenly the right one materializes. That might be like an interference process in superspace, in the space of all possible geometries, that materializes into a short wormhole, and it doesn't have a classical description as a wormhole shrinking completely. So that happens in ordinary quantum mechanics, and it also happened here. Okay, let's see. One more fun thing here. So Bob can get the message. If he gets a message and jumps in, does not see the message inside. Okay? If Alice decides to do what she originally was doing, of sending a robot and putting the message here, right? So the message is now here. If Bob does this whole procedure, what he will get is the empty robot, right? But not the message. Okay? So he does not get the message. If he decides to jump in, he will see the message, but not, he will not get it at this point. Bob, when he gets the robot, he can take the empty robot outside the geometry. He can extract it, and then run the system backwards without the robot. So the robot was doing this, and he extracts, well, by this shockwave, he extracts the robot, and now takes this geometry and evolves it backwards in time, and eventually, when he does that, there will be no robot here, so the message was up there when he does that. When he evolves this backwards in time, the message does not encounter the robot, and Bob can extract it, and then can go and jump in. So anyway, so there are all these twists and fun things you could think about. But maybe that was too fast. Okay, I want to end up with some more words on this traversable wormhole. So far, we consider a situation where we turn on the interaction at equal to 0, but we could, of course, have an interaction which exists for all times between the left and the right. And in this picture where we have the two boundaries, if we arrange the strength of the interaction appropriately, we can make sure the two boundaries are neither approaching infinity or going inwards. And turns out I'm not proving this, but you can find this as a stable solution. And in this case, you get a wormhole that is eternally traversable. So you can go from the left to the right, and the right to the left, and so on. And you can get this both in ADS2. So this is something that works for ADS2. I didn't say it. So for ADS2 or SYK, you get the same analysis, and you can make this type of traversable wormholes whose structure and so on depends only on very general properties of the Schwarzian action. So the discussion is completely parallel in both cases. And so finally, I would like to mention, you could like to say, well, all this stuff maybe is maybe a little bit like a fairy tale, because you talk about SYK model and you talk about gravity, but it's a two-dimensional gravity, or a gravity you don't understand. And yeah, maybe there are wormholes in this case. And but you know, I'm a four-dimensional physicist. I only believe in four-dimensional gravity and in the standard model, and I don't believe in anything else. And and I only care about solutions that you can write down in the standard model. I was told such a thing by a famous physicist. So the fun thing is that you can take these ideas and transfer them to generate an interesting solution in even the standard model. So you can imagine a situation where you have two magnetically charged black holes, so two Reissner-Nostrom black holes. So these are Reissner-Nostrom, very close to extremal black holes, let's say with charge Q. Q is the magnetic charge. And they are, let's say, near each other. And then you can imagine a solution where they have a kind of wormhole. So they have a near ADS2 times S2. So ADS2 times S2 near horizon geometry. And then the fact that they are close in space-time allows them, produces some interaction between them that in the throat vision we can think of it as generating an operator of this form. And so you can get a solution like this that is fairly controllable. And maybe I don't have a lot of, well. So if you have a magnetic field and you have a fermion that is charged under the magnetic field, on this S2 you'll have some Landau levels. And the interesting thing is that, so this Q is a magnetic charge which is an integer much bigger than 1. And Q is also the degeneracy of the Landau levels, of the lowest Landau level, levels on the sphere. And so each massless fermion in the bulk gives rise to Q, effectively massless fermions in ADS2. So we automatically get a large number of fermions. Remember here we needed a large number of these operators in order to have a controlled situation. And we get that, in this case, it will go up to Q. Q is a large number. And in this way, we can get a nice controllable solution. So this is just a solution that looks like a traversable wormhole in 4 dimensions. We need to assume the 4-dimensional fermion is massless, so the whole configuration has to be very small, so that we can neglect the mass of the fermions, smaller than the Compton wavelength, so it's a very microscopic wormhole configuration, but in principle a solution also of standard physics. So you don't need to invoke anything strange to have this type of interaction and this type of wormholes. Okay. Yes?
Does the black hole being magnetically charged instead of electrically charged affect this?
Well, here we needed it to be magnetically charged so that we get this multiplication effect in the number of fields that we have. So we have an electrically charged fermion, and in a magnetic field it gives rise to Landau levels with high degeneracy. And that's, yeah.
So the interaction is transmitted by fields which live on the flux line?
Yes, so we have magnetic, so we have the magnetic flux lines that go between the two configurations. And each Landau level is somehow localized within a flux line. And so you should view it as a massless field moving along this flux line. So this part of the motion within the wormhole is like the motion of a field in ADS2. The part of the motion outside is so there is a part of the motion outside, and in some regime of parameters, this length is much longer than this one, so you can view this as very fast and setting up that kind of interaction, for example.
So you can do it with electric field if you have massless monopoles?
No, you don't need the massless monopoles. You
could do it with electric field?
You could do it. You would have to set this whole thing to be smaller than the Compton wavelength of the electron. So the distance between the two black holes has to be smaller than the Compton wavelength.
You don't need magnetic charge?
Well, you need a magnetically, okay. If you wanted to make this, you had to first create 2 magnetically charged black holes.
Yeah, I'm saying you can do it with electrically charged black holes if you have massless.
Sorry, I misunderstood you. Yes. Oh, yes, that's right. But you don't want to have this in the same theory massless, massless charged particles, because then the black hole would discharge. Right? Yeah.
What happens if there is a ionic charge? Both magnets can take it.
What you don't want to have is massless fields that are charged under the same charge that the black hole is charged, because then the black hole would discharge. And I think this is the setup that works, and maybe there are a bunch of other setups that work that come from doing duality transformations, but they are not interesting. And I don't know that of a setup that works when you have massless charged particles. If you add electric fields, then the black hole would discharge. So in the end, you have something with only magnetic fields. Yeah.
If you had such a setup in the lab, can you test it experimentally, or can you test the traversability?
Well, yes, in principle, yes, if you had it in the lab. But this is a very big if, because even though it's a solution of the equations, I didn't tell you how to make it. And so it's very small, and well, the black holes would have to be, super, well, I don't know. You would have to first make magnetic monopoles, which is very difficult, and then collapse them to black holes, and then bring the two black holes together and wait for this wormhole to form, which is, we don't know how long it would take. So for now, it's a curiosity that the solution exists. How to get to the solution with a somewhat feasible, in a feasible way is not understood. But I think it's fun that one gets the solution by thinking about this, SYK and blah, blah. So it shows that all these things are connected. It's not, it's not that you cannot apply one idea to some other problem. So. Yeah. Kerr black hole. Yeah, of course, Kerr black holes are more easily found in nature. But the Kerr black hole, in some sense, carries what I would call electric charge under rotation, right? So you can have particles that carry angular momentum, and the black hole carries the same charge. So it doesn't carry the kind of opposite or magnetic charge. So I don't know how to do this for a Kerr black hole. Yeah.
I'm confused about the picture. These are two black holes. They're not like one white and one black. I mean, there's no directionality in the wormhole?
Yeah, so no directionality. One black hole has positive magnetic charge, and the other has negative magnetic charge, right? So what has some directionality are the flux lines. So the flux lines enter in one and go out in the other. Yes?
If I wanted to try to do the setup to observe not by O left, O right, but simply O right times O right, would the stress energy tensor be quadratic in G, or would it still be linear?
Yeah, if you do O right, then you will not create this negative energy.
So it would be G squared first.
No, you could have some term, well. Well, you could, yeah, so if you do O right, you might be able to have some region here of negative energy, and then some nearby region of positive energy, right? You can have situations like this, but the net integral here of the null energy will be positive, right? So what's important is for all these traversability discussions, I didn't say, but if we want to check whether we can send a signal from the left to the right, what we really care about is the integral of the null energy, the same integral that appears in the null energy condition. We want that to be negative. And if you do only things here on the right, you cannot get it to be negative. Because in the full Hilbert space of the theory in the interior, the null energy is a positive operator, okay? And if you do the creation of just here, that's you can get that by the unitary transformation, and that will create another legal state in that Hilbert space. So, yeah.
Although there are situations where all right can throw a negative energy, and in that case would be a single-sided black hole, and, and then you can escape the black hole instead of getting a traversable wormhole.
So. Yeah, maybe I'll. So if you have a situation where you have a black hole, let's say you have a black hole produced by a brane that, let's say, collapsed here, then what Ahmed is saying is that if you here you can act with an operator O right, for example, for a field that has a two-point function that depends on the position of this brane. And then by acting with this operator, you can somehow pull the brane a little bit outwards, or some excitation that was in here could be extracted. But in this case, we don't have this full horizon going to the other side, and so we cannot apply the null energy condition that we were applying in the figure that we were erasing, that they erased. Maybe there is one point that one question that sometimes arises, and I'd like to discuss it perhaps a little more. So we said that if we have this and we send a signal from here and we send negative energy, we can extract the signal. But imagine that we let the black hole evaporate, right? And if we let the black hole evaporate, there will be negative energy going into the horizon, right? So now the question is whether this will allow us to extract this signal. So this is a kind of little puzzle, because if we view this as an entangled state, just letting this guy evaporate should not allow us to extract the signal, right? So on the face of it, it looks like there is something wrong in what I was saying, because now we set up some situation where we start with an entangled state, we do some operation on the left, with no communication, we let this guy evaporate, and then naively, it looks like we can get the signal out. So the answer is that it is true there is some negative energy flux, but when we turn this, so initially the black hole was isolated, and then we turn on the coupling that will give us Hawking radiation. When we turn on, we send a little pulse of positive energy. Okay? And something that is crucial for this is, of course, that's a little pulse, and then we get lots of negative energy coming out. But what's important is that if we write it in Kruskal coordinates, for example, let's say x plus and x minus, the null energy is the integral of that determines traversability is the integral of dx plus t plus plus, while the energy of the black hole, or the Rindler energy of the black hole, is the integral of dx plus x plus t plus plus. Okay? So what we know when we do Hawking evaporation is that we have a constant rate of this negative energy, right? But since things that are emitted at late times have a bigger value of x plus, that means a smaller value of t plus plus. Okay? So as we emit later and later, it will be a smaller value, and so a smaller contribution to this. So when we look at this expression, the one that contributes most is the first one, which is the positive one. And then there are all the negative ones that make a smaller and smaller, exponentially decreasing contribution in Rindler time. So the net answer is that Hawking evaporation does not violate the null energy condition, right? Otherwise, we would have obtained a violation of the null energy condition. But the average null energy condition is still valid on this horizon. Okay, any other questions?
Quick question about this. So it seems to me we don't really need a magnetic monopole to produce this. We can imagine like we have two black holes like without any magnetic charge. First, we let them maximum entangle. Then we let some spinning a black hole with electric charge around it. Then there will be a magnetic flux around it. And then as long as we let some flux from the third black hole go into one black hole, and it come out from the other one, and then it seems like we only need the closed loop of magnetic line.
Yes. Yeah. If you can figure out a way to do it without the magnetic black holes, that's good too. Yeah. Any other question? No one. Okay. Let's enjoy the break.